All right, I want to show you two equations here. I've mentioned this one before. Delta G under standard conditions is minus NFE. In this, delta G is the standard Gibbs energy for a reaction. N is the number of electrons transferred in a redox reaction. F is Faraday's constant. And E0, that's the cell potential for the reaction. You've also seen this equation here as well. Standard Gibbs free energy is minus RT times the natural log of the equilibrium constant for a particular reaction. What these equations allow us to do is to relate the cell potential to the equilibrium constant. Look, both of these equations are equal to the standard Gibbs energy on the left. So that means I can set this equal to this. So let's do that. Minus NF E cell, that's going to be minus RT natural log of the equilibrium constant. Since there's a negative sign on each side, we can just make both those positive. And if, let's say I have the cell potential and I want to know the equilibrium constant, well, let's get the equilibrium constant alone. I'm going to divide both sides of this equation by RT. And I end up with NF times the cell potential over RT. That's going to be the natural log of the equilibrium constant. The inverse function of the natural log is e to the power of. So by taking e to the power of this side and e to the power of this side, I can cancel those functions, and I have an expression for finding the equilibrium constant if I am given the number of electrons transferred in a electrochemical reaction, Faraday's constant, which is a constant, the cell potential, of course the physics gas constant, and the Kelvin temperature. So let's apply this equation here, or all these equations, to this particular problem. Let's say I know the cell potential for this zinc complex being reduced to zinc solid and releasing free cyanide ions. And we've seen this, reduction reaction quite a bit. We're very familiar with this and its associated cell potential. Can I, using this information, find the equilibrium constant for this overall reaction? That's an interesting question. Let's see if we can pull it off. What I'm going to do is I'm going to look at the two equations that I have and see if I can combine these to give me this overall equation. And what I'm going to try is I'm going to notice that I have, dissolved zinc on the reactant side in this half reaction, and I see dissolved zinc on this side in this half reaction. In this half reaction, I see the zinc complex on the reactant side, and I see the identical zinc complex on the product side. So that means I'm probably going to flip this reaction. So I'm just going to try that. I'll just write it up here above. Let's see, I'm going to flip this. So it's going to be solid zinc plus 4 cyanide ions. That's going to go to my zinc cyanide complex and 2 electrons. And of course I better, flip the sign. And now I'm going to add together the starred reactions. Let's see, I've got 2 electrons coming out in the first reaction and 2 electrons going in the second reaction. So those cancel. What am I left with? Well, no, I see I got zinc solid on the reactant side in the first reaction and zinc solid on the product side in the second reaction. And now, if I look at what I'm left with, I know it's a little confusing. We have to ignore this reaction here. So I'm just going to place this here. Okay. I see zinc here, 4 cyanides going to the zinc complex, and that's it, nothing else. So I've recovered this reaction by adding this one and this one. So I know the cell potential for this. That's going to be the sum of 1.26 and 0.34. What's that going to be? Let's see. 10, carry the 1, 6. If my math is good, that's a positive 1.60 volts. I just want to check to make sure that's right. That's 10, carry the 1. Yeah, that looks good. So the cell potential for this overall reaction is a positive 1.60 volts. That was a pretty fun trick. Now I want to calculate the equilibrium constant for this reaction. What is the numerical value of the equilibrium constant for this reaction? Well, here we just showed this reaction here, didn't we? So let's try it. The equilibrium constant should be equal to N, the number of electrons transferred. Let's go back and check. There were 2, weren't there? Yep. There were 2 electrons necessary to balance the reaction. All right. So I'm going to write that's equal to 2 times Faraday's constant, 96,485, what's that, coulombs per mole, times the cell potential, which is 1.60 volts. I'm going to write the volt as a joule per coulomb. It's the same thing as a volt. I'll divide this by the physics gas constant, 8.314 joules per mole per Kelvin. And then I need to multiply that by the temperature. And since we're doing standard conditions, we'll just do 298 Kelvin. Well, equilibrium constants are unitless, so all these units better cancel out. So let's see. On the numerator, I have a coulomb and a coulomb here on the denominator. I have an inverse mole on the numerator that cancels an inverse mole on the denominator. I have a joule on the numerator that cancels a joule on the denominator. And on the denominator, I both have an inverse Kelvin and a Kelvin. So everything cancels out, and all I got to do is add everything together. Oh, I almost forgot. I better take e to the power of whatever this is, this whole thing, when I'm done. That would have been a big boo-boo. All right, let's add all this up, see what we got. Okay, 2 times 96,485 times 1.6 divided by 8.314 divided by 298. So I get 124.6. So I need to take e to the power of 124.6. So let's see. I'm going to do this button here, e to the x. Holy cow, that's a big number. 1.32 times 10 to the 54th. And we would expect this reaction here to be very strongly pushed in this direction with such a large equilibrium constant. And that relates to, yes, a positive cell potential tells us that this reaction is spontaneous in the forward direction.